Many times we want to study for properties of sequences, sequences in R at the moment. It could be that we want to see if the sequence behaves periodically, or we want to study for long-term behavior, and that is the topic in this clip. So we want to look at convergence of sequence. So by definition, what does it mean? I will just plug in the definition here and I will discuss it later on. So what does it mean that a sequence is convergent? Well, a sequence is convergent if the elements tend to a certain value. So here is the value R and or L and AN has a limit or converges to the element L in R if I can make the elements arbitrarily close to L, which means that for each epsilon larger than 0, there exists an index large enough so that we take even larger index numbers n, small larger than capital N, that the difference in absolute value, the difference of an minus L in absolute value, is smaller than this bound epsilon. This means that for any, by varying over all epsilon, I can always specify indices such that the a and r smaller than this epsilon. And by varying these epsilons, I can thus make the elements become arbitrarily close to L. So in that sense, I will call L the limit of the sequence AN. So in other words, the elements get arbitrarily close to L by picking the index numbers large enough. Yeah, and in that sense, if there is such a number L to which the AN converge, we will denote it as L is the limit. We write it as such, is the limit for n to infinity AN. So for example, here we have the sequence AN equals 1 over n minus 1. So if we just write down some elements, right? So we have some elements, and which are these elements? Well, the sequence starts not with 1, but with 2. And there we have a value 1. And then for n equals 3, we have a half, etc. 1/3, 1/4, etc. So it seems that this sequence, when n gets arbitrarily large, that this sequence tends to 0, right? So I will now show, it will show that using the definition I discussed before, that we can show that the limit for n to infinity of this sequence AN equals 0. Right? So what we need to do is showing that for any epsilon, right? So let's return to the definition. So we have to show that for each epsilon larger than 0, there exists an index number n in the natural numbers such that for larger index numbers than this capital N, the difference between AN and L in absolute value is smaller equal than epsilon. So we start by picking an epsilon larger than 0 and then point out that we can find such an n. So that will be our strategy. So let's start by picking at first an epsilon, which is an arbitrary number larger than 0, but in the remainder it is a fixed number. And then we continue. So let's see if we write down the absolute value of the difference from AN and L. And yeah, what is L? Well, L is supposed to be the 0 here, right? So it should be the 0. So that should be L. That an minus L, well, we suspect that this is the limit. And we have to show that an minus L, which is the an, and if we put absolute value signs around it, then we get the absolute value of an by picking n large enough that this this term an absolute, is smaller equal than epsilon. Well, can we do this? Okay, so we have to make sure that this value is smaller than epsilon. Okay, this means that the absolute value of 1 over n minus 1 is smaller equal than epsilon. Yeah, okay, but we can leave out the absolute value signs because 1 over n minus 1 for n is 2, 3, 4, etc. is larger than 0. So this is just equivalent with stating that 1 over n minus 1 is smaller equal than epsilon. All right, so now we just take the reciprocals on the left hand side and the right hand side, and so that we get m minus 1 is larger equal than 1 over epsilon, right? So the inequality is reversed, right? So m minus 1 is larger equal 1 over epsilon, which means that n is larger equal 1 over 1 over epsilon plus 1. So if we just take n larger than this number, 1 plus 1 over epsilon, then we're doing okay, right? Yeah, okay, but we want to find a natural number, right? So an index number, and this number here, 1 plus 1 over epsilon, is just a real, right? Since the epsilon is just taking is just an arbitrary number larger than 0. So we want to round off this element. If we just round off this element above, then n larger than this rounded off value would suffice. Okay, okay, that's the second stage, what we do. So let's define the capital N. We have an index which is the entier of 1 plus 1 over epsilon. That's just the rounded off. We round off this number 1 plus 1 over epsilon to the smallest natural number larger than this a real number, and that's our index n, our capital index n, our capital N. Then what we get is, yeah, so this is called the entier of 1 plus 1 over epsilon. Then what we get is, if we take a larger, if you take n larger than this capital N, then what we have is n larger than the entier of 1 over n plus 1 over epsilon, is larger, of course, than 1 plus 1 over epsilon, because the entier is the is larger than without the entier. Okay, so now we can basically reverse those steps we have here. So n is larger equal than 1 over 1 plus 1 over epsilon, and then we here n minus 1 is larger equal than 1 over epsilon. That means that this one is smaller than epsilon, etc., etc. So we find, what we do find in the end is that an minus 0 absolute equals 1 over n minus 1, and which is smaller equal than epsilon. And this is exactly what we wanted to show. So in this case, we indeed have shown that the limit of n going to infinity of the sequence an equals 0. Okay, another example. This is an important example. This is the geometric sequence where r is a number in between minus 1 and 1. So the absolute value of r is smaller than 1. Yeah, so that's here. So this is a real number r, which is in between minus 1 and 1, and we can form the sequence like so. This is the sequence of r to the power n, and this is called the geometric sequence. Okay, So let's see where we end up. We will show that for any such r, that the limit of n to infinity of an equals 0. Well, that's not too wild, since if we would take r equals 2 1/2, then we build the sequence of 1/2 to the power 1, which is a half to the power 2, which is 1/4, and we get 1/8, 1/16, and so forth, so which clearly goes to 0. Here we will just take a formal proof, formal steps in showing that the limit is 0. So in our definition that we've seen, we'll take L equal to 0. Again, we take the same step. The first step is assuming an epsilon larger than 0, which accounts for the error, right? So we want a number epsilon larger than 0, which is the error term. So we now have to make sure that we can take indices large enough such that the difference, the absolute value of the difference between an and L, is smaller than epsilon for all larger indices. So that's what we're going to do. So we start off again by looking at an minus the thing that we think is the limit. And we show that this is going to get arbitrarily small by taking n large enough. In particular, we show that by taking n large enough, in this case, we get a term here. This term is smaller equal than this epsilon. All right, so let's do so. So we just plug in the definition of an. The 0, of course, we can leave out. Then we see that this is no more than the absolute value of r to the power n. Okay, so we continue. So in particular, an minus 0 is smaller equal than epsilon. That means that the absolute value of r to the power n should be smaller equal than epsilon. Okay, but now we have, since r absolute is a positive number and epsilon is a positive number, we can take logs on both sides. And the reason that we want to do it is that we want this exponent n to come down. So what we do is we take the log on the left hand side, the natural logarithm, and on the right hand side we take the natural logarithm. And then we see that by using the calculation rules with the logs, that on the left hand side we get n times the natural logarithm of the ln of the absolute value of r is smaller equal than ln of epsilon. And why is this? Well, ln is a monotonically increasing function, as you know, so we keep the same ordering of these numbers. So n times the ln of absolute value of r is smaller equal than the natural logarithm of epsilon. Okay, we want to have a minimal value of n such that these relations hold. So we see that if we just take n larger or equal than ln of epsilon divided by ln r of the absolute value of r, then we're done. You might wonder why this inequality switched or flipped. Do you see why? Well, we know that r is in between 0 and 1. So the ln of the absolute value of r is negative. So if we divide by a negative number on the left-hand side and the right-hand side, we see that this inequality flips. So we get n larger equal than the ln of epsilon divided by the ln of r absolute. Yes? Okay, so if we now continue our story, so the second phase is defining our natural number, right? So our capital N, the index, such that if I take a larger index, then everything goes smooth and we get an minus 0 absolute smaller equal than epsilon. So again, we take not the exact number, because we have here an idea what this number should be. It's the ln of epsilon divided by the ln of r absolute. but this is just a real number. We want an index. So we just round off this term to the nearest index that is larger, which would be the entier of ln epsilon divided by the absolute value ln of the absolute value of r. Yeah, and then we proceed just as before. If we take an index larger than n, then we can continue the story. Then n is larger than the entier of the ln epsilon divided by the ln of r epsilon, r absolute, which is larger, of course, than the term without the entier function. And if we have that one, we can just follow the path back, right? So here we see a double implication sign. Here we see a double implication sign. So this statement here is equivalent in the end to the statement that an minus 0 is smaller equal than epsilon, right? So I will do it a little bit fast. So here we get all the terms, so we can just go back. The complete story can be followed back, traced back, as we already did the work above. So we in the end get that an minus l absolute is smaller equal than epsilon, and this is what we needed to show. So indeed, the limit of this geometric sequence is 0, at least if r absolute is smaller than 1.